Welcome to less obvious L'Hopital's rule cases. So L'Hopital's rule came in for a couple indeterminate forms. So we used L'Hopital's rule for the cases where a limit as x approaches c of some function f of x went to either 0 over 0 or infinity over infinity, right? But we do have other indeterminate forms. So we have other indeterminate forms. And those could be, if we have infinity minus infinity, that could land on a specific number. It could be, or it could be infinite. We could also have a case where we do 1 raised to the infinity, 0 raised to the 0th, or 0 times infinity. All of these are cases where kind of we have contradictory things happening, right? So 1 raised to any power is 1, but things raised to the infinite power are typically either infinity or it goes to 0 if we're looking at fractions, things less than 1. 0 raised to any power is usually 0, but then anything raised to the 0th power is typically 1. And then again, 0 times anything is usually 0. And then anything times infinity is usually infinity. So we have these two pieces that are counteracting each other, and we need to figure out sort of what is happening. One more that I missed is if we have infinity raised to the 0th power. So as numbers get large, when we raise them to powers, it's typically going to be a large value, but then when we raise to the 0th power, it's usually going to 1. Again, we have these two sort of competing potential limits. So what happens when they happen together? So again, none of these look like L'Hopital's rule. So the idea here is that if we have one of these other indeterminate forms, we want to manipulate the limit until we essentially see, until L'Hopital's rule essentially falls out. So if we have one of these other indeterminate forms, then we want to manipulate algebraically until L'Hopital's rule applies. So let's go ahead and consider the limit. Oh, sorry, this should be the limit as x goes to 1. I changed the problems as I was writing this. So let's go ahead and evaluate the limit as x goes to 1 of x over x minus 1 minus 1 over natural log of x. So if we plug in 1, we'd be looking at 1 over 1 minus 1, which is 0, minus 1 over natural log of 1, which is also 0. So this is a case where we're looking at infinity minus infinity. So from here, we want to manipulate this. So when we're subtracting fractions, we might as well just do the fraction subtraction, give a common denominator, so that we are only working with one fraction. So let's combine this to one fraction. So we have our common denominator. Of x minus 1 times the natural log of x. So that first fraction we should multiply by natural log. So we're looking at the limit as x approaches 1 of x times the natural log of x all over x minus 1 times the natural log of x. And then the next one, we're missing a factor of x minus 1. So we go to 1 times x minus 1 all over x minus 1 times the natural log of x. And from here, this becomes the limit as x approaches 1 of up top, we would have x times the natural log of x. And then we would subtract x, and then minus -1 would become plus 1 all over x minus 1 times the natural log of x. So again, if we plug in 1, that denominator is definitely 0. We'd have 0 times 0. And then up top, 1 times the natural log of x is 0. Minus 1 plus 1, then we go to 0. So this is a 0 over 0 situation. So we can go ahead and apply L'Hopital's rule. We take the derivative of the top and the bottom. We are looking at the limit as x approaches 1. We will have a bit of a product rule here. So x times natural log of x, we do the derivative of x as 1 times natural log of x, and then plus x times the derivative of natural log of x is 1 over x. And then minus x becomes minus 1. And down below, again, we have a product rule. That first derivative is 1 times the natural log of x. And then plus x minus 1 times 1 over x. I need to give myself a little more space. This is equivalent to the limit as x approaches 1 of the natural log of x all over the natural log of x plus x minus 1 over x. Now this again is a 0 over 0 situation. I'm going to make my life a little easier by clearing that fraction in the denominator. So let's go ahead and just multiply both the denominator and the numerator by x. That's essentially equivalent to multiplying by 1. Just so that to clear that fraction in the denominator. So I'm just going to note. So this was again a 0 over 0 situation, right? We could differentiate as is, or we can go ahead and clear that x from the denominator. So let's multiply by x over x to clear the fraction in the denominator. So at this point, we'll have the limit as x approaches 1 of x times the natural log of x all over x times the natural log of x plus x minus 1 over x, or the limit as x approaches 1 of x times the natural log of x over x times the natural log of x plus x minus 1. So this was just to kind of change the form. It happens to make the derivative a little simpler and make the next L'Hopital's rule application give us what we want. So once again, this does go to 0 over 0 if we plug in 1. So we'll go ahead and apply L'Hopital's rule one more time. So we have the limit as x approaches 1. I'm just going to shift this up so that it's where we're applying it. We have the limit as x approaches 1. Again, this became 1 times the natural log of x plus x times 1 over x. And then again, we have the natural log of x plus x times 1 over x, and then plus 1 down below, right? Or equivalently, the limit as x approaches 1 of the natural log of x plus 1 over the natural log of x plus 2. And now if we take this limit as our x goes to 1, that becomes 0 plus 1 over 0 plus 2, better known as 1/2. So in this case, we were able to manipulate our subtraction of infinities into a fraction that was went to 0 over 0. Applied L'Hopital's rule, did a little algebraic manipulation, still had 0 over 0, applied L'Hopital's rule again, and we were able to evaluate the limit. Next up, we'll go ahead and take a look at a product. So if we look at the limit as x goes to 0 from the positive side of x times natural log of x, this case, we're going to get a 0 times a negative infinity. Right? And so this has two conflicting pieces of the product, one trying to pull things to 0, one trying to pull things to negative infinity. So we're going to go ahead and just rearrange this. We can always change a product to a quotient. So we're going to change this to the limit as x approaches 0 from the positive side of the natural log of x over 1 over x. These are equivalent to each other. We just changed the product to a quotient, right? Once we've done that, this is we'd have a negative infinity over infinity situation. So L'Hopital's rule does apply. So at this point, let's go ahead and apply L'Hopital's rule. Take the derivative of the top and the bottom. We have the limit as x approaches 0 from the positive side. The derivative, oh, I need to update my screen in a moment. All right, so from here, again, we're taking the limit as x approaches 0 from the positive side. We're applying L'Hopital's rule. The derivative of natural log of x is 1 over x. And then 1 over x down below, that's x to the negative 1. We wind up with negative 1 over x squared. We can go ahead and then rearrange this. This is still infinity over infinity case. But we can rearrange it. So this is the limit as x approaches 0 from the positive side of 1 over x divided by negative 1 over x squared is the same as multiplying by negative x squared over 1. And so we're looking at the limit as x approaches 0 from the positive side of, this is just negative x. And so we wind up getting 0. Taking one more limit, let's go ahead and evaluate the limit as x approaches 0 from the positive side of x to the x squared. So what we are going to do here is we are going to take advantage of natural logs and then be able to pull a power out front. So we're going to use natural log to pull powers out front. So if we want to have an equivalent statement, we can take advantage of the fact that e to the natural log of x is the equivalent of x. And so we can take this as equivalent to doing the limit as x approaches 0 from the positive side of e to the natural log of x to the x squared. Right? Again, e to the natural log, those are inverses of each other. So if we apply them, that is just the same as x to the x squared. Now, if we pull that x squared out front, we're looking at the limit as x approaches 0 from the positive side of e to the x squared times the natural log of x. And from here, we can actually push the limit inside of the e to the whatever function. So this becomes e to the limit as x approaches 0 from the positive side of x squared times natural log of x. So we can push a limit inside of a continuous function. So from here to here, we pushed the limit inside the continuous function. Essentially, we pushed it inside e to the u. So at this point now, we just need to evaluate that limit. So let's go ahead and focus on this limit. So the limit as x approaches 0 from the positive side of x squared times natural log of x. This is again a 0 times infinity case or a 0 times negative infinity case. We can do the same manipulation as last time. So this is the limit as x approaches 0 from the positive side of natural log of x over 1 over x squared. This is now a negative infinity over infinity situation. We can go ahead and apply L'Hopital's rule. And taking the derivative of the top and the bottom. Up top, natural log of x goes to 1 over x. Down below, 1 over x squared is just x to the negative 2. This becomes negative 2 over x cubed. This is still an infinity over negative infinity case, but we can now manipulate. So this is the same thing as the limit as x approaches 0 from the positive side of 1 over x times negative x cubed over 2. And this becomes the limit as x approaches 0 from the positive side of negative x squared over 2 if we simplify. That goes to 0. So this was our exponent. Right? So now what we can do is we can go back to our original e to the. So we had that our original limit as x approaches 0 from the positive side of x to the x squared. This was equal to the limit as x or this was equal to what we found before, e to the limit as x approaches 0 from the positive side of x squared times natural log of x. We just found that limit to be 0. So this is equal to e to the 0th. Better known as 1. So when we do these manipulations, indeterminate form may or may not give you a number. It's possible that when you do the manipulation and apply L'Hopital's rule, that we wind up getting infinity or negative infinity, or possibly even just a limit that doesn't exist at all. But we can do the manipulation to at least make it appear that we're working with a L'Hopital's rule situation, perform L'Hopital's rule, and then see what we get.